on the final?
Yeah.
Okay.
The cheat sheets will be allowed, like for all of the exams. Yeah. Yep. Uh-huh.
Just, you wouldn't need to do that.
Oh, what?
You wouldn't need to do that.
Yeah.
But any
So
comments?
so there will be 10 problem sets, right? The last problem set will be about mediation. So so if you feel good about the other problem sets, including fixed effects and panel, then you don't really have to do the last one because the lowest grade will be dropped.
But that will be that material, but the deviation analysis is going to be on the final exam.
Uh-huh.
Okay.
Yes. Any other questions? And the last thing is, if you decide to drop one of the problem sets, please let me know. Especially like if it's regarding IV or problem set 9 or 10, because you might need the problem answer keys before the exams, right? So if you decide to drop one of the problem sets, you should let me know. So we can talk about it.
So you have problems at 7 due on there twice, on the 15th and the 29th.
The second one should be PSA. I think on the 29th, right?
Yeah, so what is due on the 29th?
April
29th.
29th, it should be PSA.
Oh, PSA.
Yeah.
Yeah.
And-
PSA 8 due. Sorry
Oh,
about
and
that.
sorry.
This is actually
Sorry.
8. Yeah. All right. Great. Let's move on to the substantive topics. Or the section. All right. So we covered generalized linear models for limited dependent variables, right? So it's basically generalized linear models is the generalization of ordinary linear regression for continuous dependent variables or unlimited dependent variables, right? But then we are generalizing this linear regression so that we can analyze limited dependent variables. So the question is, what is a limited dependent variable? Right? It is defined as a variable with a restricted range, which includes censored and categorical variables. Censored variables examples would include income variables with an unlimited top category. So there's an income variable with a top coded values in it. Does that make sense? So so after say $1 million, there are some people, right? But you are, for the sake of identity and confidentiality and stuff like that, you are top coding people as $1 million for your income, annual income. Okay, so that's censoring. So
Even if they are above $1 million.
yeah,
Mhm.
in reality, they are above $1 million, but they are coded as $1 million, and you don't know what the real values are.
Mhm.
And then that's an example of limited dependent variable because it's the range of the variable is now limited in that sense. Good. And for categorical variables, they include binary, death or being alive, ordinal, the level of happiness in 5 ordinal terms, very happy, happy, somewhat, not really unhappy, and very unhappy. That kind of ordinal variables. And there is multinomial categorical variables or nominal variables such as employment status. You work in a part-time job, full-time job, full-time job, or you're not employed or something like that. There are more than 2 categories in the variable. But here we focus on the analysis of binary variables in this class. But still, there are other techniques for ordinal variables and multinomial variables. Good. So this is the limited dependent variable. So we're trying to analyze that that type of variables as dependent variables. Okay. Actually, FYI 1 is this is FYI, but you may heard of the term truncation. When some of the individuals are missing due to the range issue, for example, those who earn more than $1 million were not surveyed for some reason, and in this case, a source of selection bias, if it's ignored, it can be a source of selection bias if it's ignored, and it's different from censoring because they literally don't exist. Does that make sense? So instead of top coding these people, they did not survey these people in the data. That's truncation. Good. So there is a slight difference between censoring and truncation. And there's another issue of attrition. This is basically an example of it will be sample non-response. This can be considered as a type of censoring. It'll be important for event history analysis and stuff like that, but this is just FYI thing for now in this class. Good. Any questions? Yes.
You break about why the ordinal variable is to be categorical or just like
So for a happiness, variable, if it's measured by 5 categories, right? That could be considered as ordinal variable, right? But if it's really measured from 0 to 10, 0 to 100, and then you are basically like measuring the level of happiness in terms of answering the level of happiness between the level of 0 and then that of 100, then the categories are too detailed enough. The categories are detailed enough to treat the variable as if it were a continuous variable. Does that make sense?
So those
But
5
still
scale,
it's-
those 5 scale variables is not enough to be detailed.
Right. Not enough, not detailed enough to treat it as if it were a continuous variable. So you may have heard of scales from 361, right? You added some variables to make a score or whatever, and then you added some responses from multiple answers, right? And then the range becomes from say 0 to 25, for example, right? If that's the case, we are saying that it's the range, the categories are detailed enough to believe that we can treat it as if it were a continuous variable, and then the results won't be that different, basically.
In my understanding, like ordinal variable is ordinal because the range between 1 and 2 is not necessarily the same with the range between 2 and 3.
Yes.
So that's the definition of the ordinal variable.
Yeah, that is true. But so you're making a lot of assumptions in treating this scale as a basically continuous variable, right? If you are making a scale, having a scale, then you're saying that it is okay to believe that this is a continuous variable because the categories are detailed to treat a continuous variable, and the intervals between the values are exactly reflecting the exact same intervals in real life. So you're making a lot of assumptions when you're creating a scale. Yeah. So basically, if you have one question and with 5 categories, such as happiness, then you should definitely use ordinal logic model. Yeah. Good. All right. And so if to analyze limited different variables, you need the generalization of ordinal regression model, but why? That is the question. So it is to resolve problems with the OLS estimation of limited dependent variables. So if you run the same ordinal regression model with limited dependent variables, then there could be 3 problems. The first one is specifically for censoring situation only, not all limited dependent variables. Does that make sense? Yeah. But one-side censoring to be exact. It can lead to the attenuation of the beta coefficient. So if they were not censored, the regression would have been this one. Regression line would have been this one. But because they were censored, now the estimated regression looks like that. Does that make sense? Yeah. So that is the first problem of OLS estimation of limited dependent variables. Okay. And the second problem is there could be some predicted values out of the proper range of the dependent variable. For example, if your dependent variable is binary, for example, you graduated from high school or not, right? Then predicted values or predicted probability of high school graduation could be out of 0 or 1. Does that make sense? If you run an OLS estimation, OLS regression model, because even though there are observations look like that look like that, right? But the predicted value of x being, say, 20 will be here, right? So the predicted value when x is 20 is higher than 1, which is out of the proper range of the dependent variable we're analyzing. Good, does that make sense? Yeah, that is the second problem. And then related, the third problem is heteroscedastic errors. So as you can see, error here is larger than here, right? So the variance of the errors can be different across the level of x's as a result. Does that make sense? Yeah. All right. So there are these three problems, one of which is specifically applied to one-side censoring, but still. So you are trying to resolve that problem. So the question is, how would we do it? We're learning these strategies to resolve this situation. So we are using the concept that's called link function. So now, instead of using y, you are putting y into some sort of function, and then use that as the dependent variable. So that way, the range of this part, the right side of the equation, can have an unlimited range, even though y has a limited range. Good. Does that make sense? For example, logit function is one of the examples. So logit function is log of p divided by 1 minus p. I'll explain that in more detail, but it looks like that, where p is the probability of y being 1. The probability of, say, graduating from high school. Does that make sense? And then this log part makes it have unlimited bound. So even though p divided by 1 minus p would always be positive, right? It would be always positive. But if you put the log out of it, then you would have the range of negative infinity to positive infinity. Good. How are you guys familiar with the, how much are you guys familiar with logs? Like, I mean, are you guys familiar with logs? Sort of. All right. Okay. So how should I explain? So it's basically inverse of powers. So so there is this a number called E, which is also called Euler's number. This is nothing special. I mean, it's a special number, but it's a number. It's about 2.7, basically. And if you square it, you are basically multiplying it by 2 times, right? Does that make sense? Yeah. If you put the log into this number, then you are getting 2. So you are, the log, natural log, is basically what lets you get this this here, this part here, the power part. You guys know the concept of power, right? Yeah. So the log here is that you have the power part as a result. Good. Any questions? Nope. All right. A nature of characteristic of logs here is that even though, so basically, even though it's all positive here, if you put the log in it, then you would have the boundary of negative infinity to. Does that make sense? Because you know, e to whatever number a becomes b, and it's always positive, right? What regardless of whether a is negative or positive. I'm assuming you guys know much about power. Okay. And then if you put the log in it, oh, sorry. Yeah, I'll stop at that. Does that make sense? Good. Yeah. All right. Okay. So yeah, that's the an example of link function. So again, the point of using a link function is let a limited dependent variable to have an unlimited range. That's the solution here to resolve the concern that we just saw earlier. Good. So actually, if this is identity function, G is the identity function, which means y. If you put the y in it, then you will get y as a result. That's the identity function. If that's the case, it'll be exactly like ordinary regression logic, right? Yeah. The estimation method is the most popular one is NLE, but because OLS only works well for identity link function, which means that it OLS only works well with the continuous dependent variables. I'll explain why this is the case in a minute, but yeah, just to put that out there. Yeah. So, and then the components, as you can see, are random components, and this is the link function, and this is the systematic part. So what's added is basically the presence of a link function, and that's it, right? And then the minor modifications in the error distributions assumptions. So what's different from ordinary linear regression is that you have a wider variety of choices in the assumptions of random component and the link function. So you are postulating different error distribution and adding a link function. Good. I'll explain. I'll give you an example with the logistic regression as well. There are different link functions and their usages. Tobit is used when there is a one-sided censoring, and probit and logit are used when they're these link functions when their the outcome is binary. There are subtle differences between the two in the sense that probit uses probability and logit uses odds, basically. But they yield the same beta coefficients if the probit ones are multiplied by 1.18 in the probability scale. If you change the odds scale to probability scale, they are basically the same things. But so sociologists are obsessed with odds for some reasons, actually. Felix said that they're basically the same thing, and that's true. But there are some merits to odds as well. I'm sure Felix wanted to make things simple, so that's why I mentioned that. But there are some reasons to use odds, especially if you're working with mobility tables. So you should definitely talk to me if you're working with mobility tables and stuff like that to see the merits behind the odds. But for this class, I would say they're basically the same things in the probability scale. Does that make sense? Am I confusing you or? Good. All right. Okay. There is other link functions such as Poisson binomial and negative binomial. They speaks to the situation where the dependent variable is a count variable. So, for example, the number of children born in the household within the recent 10 years, or the number of typos in a book, or the number of people who get into the elevator in 1 hour, basically. So in that case, the variable is not negative by nature, right? So it has a boundary. That means that you need basically a link function to deal with this situation. Does that make sense? And there are many more. All right, good. Any questions so far? Let's talk about logistic regression model. So in logistic regression model, the dependent variable here is the logit of P, which is also log of odds, and this is log P divided by O minus P. And they are regressed on X variable. So as you can see, this is a regression model. So, but with a logistic link function right here, okay, and errors with logistic distribution. So errors are assumed to follow a logistic distribution, which resembles a normal distribution, but has a thicker tails. So basically normal, like slightly different from normal, but has slightly thicker tails for some reason. So, but you don't really have to know what logistic distribution is, or something. Just you can just know this fact without knowing what a logistic distribution is. Yes. Any questions? Nope. But you have to know logistic link function, which is this one. So let's talk about logit, odds, and all that fun terminologies. So I'll give you an example. So let's say we have a binary variable that whether one agrees with the statement that it'll be much better for everyone when men goes to work for pay and women stays at home to raise their children. Okay. Men, women, total 20, 10, oh, shoot. $20, $10, 20, 50, 50, 70, 100, 40, 60. Right? So we have this table. Right? So in that case, probability of agreement, probability of agreeing with the statement for men. This is nothing like serious. This just means for men. Okay. Regarding men only. What would that be? 20 out of 40, which is 1 and 2. Good. Probability of agree given women will be 1 in 6. This is pretty straightforward, right? So far. In odds, can I erase this? Odds of agree for men is 1 divided by 2, which was the probability of agreeing with the statement for men. 1 minus the probability. P divided by 1 minus P. So basically it means probability, like the ratio between agreeing versus disagreeing. Agreement and disagreement. Does that make sense? Yeah. So the probability of agreement divided by the probability of disagreement. And then you are making a ratio out of it. Good. Which is 1. So you should interpret this as that there is 1-to-1 odds of agreeing to agree with the statement for men. Does that make sense? No? All good? Yeah. All right. And odds agree for women was 1 divided by 6. So it's 1 in 5. So you are saying that the odds of agreeing with the statement is 1 divided by 5 to 1. Or 1 to 5. Does that make sense? Yeah. And the logit, which is log odds here, logit here is log of 1, which is 0 actually. the calculator will calculate it for you. So I won't cover too much about the calculation of log, but the result is this one. Good. And logit for women is about negative 0.69. Good. Then let's see what is the so that's the concept of probability, odds, and logit, right? So now we're moving on to what is the effect of gender on logit and odds. Good. So logit difference is logit difference is negative 0.699, which means that being a woman is associated with negative 0.699 decrease in the logit of agreeing with this statement. I have to make a note that log of A minus B, oh sorry, A divided by B is log A, log B. So in our case, log A was odds of agreeing for women, right? And the B was log of odds of agreeing for men. Okay. If we apply that, then logit difference is same. It's a synonym for log odds ratio, where this is log of odds agree for men and divided by odds agree for women and men. Good. Does that make sense so far? Or good? Yeah. All right. So it means that log odds ratio is the log of odds ratio. Good. So you calculated that, right? The logit difference, which is log odds ratio, right? And then if you exponentiate this log odds ratio, right? It is the same thing as e to the log of odds ratio, which becomes odds ratio. So that's why the odds ratio is e to the 6 negative 0.699, which is 1 in 5. Good. Any questions?
This might not be like fully formed, but in terms of discussing this in like a research context, what
Mhm.
technology would be preferred? What would be like the most common?
That'll be all covered in the second half of
Okay,
the
gotcha.
section, actually. Yeah, I have some recommendations actually. Yeah, yeah. Good. All right. And then now that we you know laid out all the terminologies, let's cover an example of regression, logistic regression. So let's see, we have logit of P, 5, age, and E, where the probability means the employment probability, the probability of employment. Okay. And so in this situation, when you observe here is this one. Probability, this is probability of y being 1, i.e. probability of being employed. So we have these observations, right? They have either 0 or 1 as the values for the probability. And then we are trying to estimate the latent tendency of employment behind this observed outcomes. And we are assuming that the latent tendency, if latent tendency is, say, is higher than 0.5, then we are observing y is y1, and if this is lower than 0.5, then y is 0. This threshold is completely arbitrary, so that's why you should not trust the intercept of logistic regression model. But this is not, intercepts are not really important in the first place, so so they're not really important. Okay, so we are trying to fit this non-linear curve based on our observations. How one does that is the question, right? So to do that, we are putting log, or changing, you're putting the link function of logistic function, basically. And then now the scale here is not bound from 0 to 1, but from negative infinity to infinity. And now you are assuming this is the latent propensity of employment. Good. And observations are right here. They are at the positive infinity because each value has a p value, the p of 1, for example, right? And that makes log of odds is this one. Does that make sense here? Okay, good. So for this one, they would be negative infinity. All right. So, yeah, right. And then, based off of these observations, you are getting this regression. You're fitting this regression line by MLE, that the process of which will not be discussed in the class, but I'm happy to discuss that in my office hours. Good. And the slope here is 0.1, just like the regression. And the intercept is negative 0.5. Good. And let's say we are looking at the predicted logit at the age of 25. Let's say that. And then it would be, the predicted logit would be negative 0.25, because if you plug in 25 here, then the result would be negative 0.25. If you plug in the 25 here, right? Does that make sense? Yeah. And it can be translated into the probability scale, because logit of employment at age 25 is negative 0.25, right? And you are putting it as this one. They're the same thing, right? Logit is log odds at the age of 25. Then you are e to the negative 0.25. So that's how you can cancel out the logs, right? If you exponentiate both sides of the equation, then you would have this one, right? Again, exponentiate something cancels out the log part. Good. And if I can move here, if you multiply 1 minus p hat to both sides of the equation, then it becomes p hat e to the negative 0.25 and e to the negative 0.25 p hat. Right? And if you move this part to the other side of the the equation, then it becomes this one. And this is same as this one. As a result, P becomes e to the negative 0.25, 1 plus e. If you divide this number on both numerator and the denominator, then it becomes 1 divided by 1 plus e to the 0.25, which will be about 0.438. So it can be translated into the predicted probability at the age of 25. So it is pretty complicated process, right? Or you can use the shortcut, which is the formula of E. Oh, sorry. P hat is 1 divided by 1 plus E minus XP. So you are plugging in the minus 1 multiplied by the predicted logit. XB represents the predicted logit at the X value. Any questions so far? All right, good. So you are again in the logistic regression model, you are translating this observed y's into the latent y latent tendency of employment by assuming that the link function p, logit of p, is the latent tendency of employment. You're assuming that. And you are estimating a slope, regression line, and then translate that into the predicted probabilities. If you translate that, it'll be a non-linear curve. Does that make sense? See the flow of the logic, or no? Right. There are, for estimation methods, OLS is not available because each data point has positively or negative infinite odds. Thus, OLS residuals cannot be estimated. So for OLS regression, you would have calculated this residual, right? And then you are trying to minimize the squared residuals, right? But in this case, they're all infinite. So you cannot really calculate OLS estimated regression line. You cannot really obtain that line. So that's why you want to use MLE. So MLE is the most popular one among others. And an important point here is that the variance of the error term is fixed to 3.29. That's because it's the the variance of error term is fixed to 3.29 when error term is assumed to follow a standard logistic regression, logistic distribution. I can explain that in more detail in a minute, but so the gist of it is basically it really comes from the nature of these observations. They're infinite, right? They're not. So the thing about being infinite is that it's fixed. It's not a fixed number, right? So it's a state. So the scale of this one can be anything, really, because they are unique states. Does that make sense? So even though it's logit, the y asterisk scale can be anything. So that's why you wanna use assume a standard logistic distribution to fix the variance of error term. That'll make the scale fixed, and then that enables you to get a regression. Good. So it has to be fixed for identification of the identification of a regression model. Does that make sense? Good. Yeah. I'll explain that in more detail and the consequences of that. So, wow, we have a lot of things to do, but I have to pick up the answer keys to the problem set 5. So we can take like 3 minutes and come back.
Did you get that message? You may not agree.
Yeah.
All right. Let's start again. So, I. Okay. So, I should focus on the interpretations, but okay. So, I can explain them in more detail if time allows that. But so basically, in logistic regression model, the slopes are identified up to scale, as I mentioned earlier. So so the slopes can be really anything, unless the variance of the error term is fixed. Okay. So so basically, that's the reason why beta coefficients are identified only when they're divided by the unknown scale factor, because this, by the scale factor, it means that the proportion of the true variance divided by the fixed amount of variance. So two. Where is right? Right. So let's add this. Alright. So let's say there's a E with a true variance. But then for the identification, it is fixed to epsilon with the variance of 3.29. And you are multiplying S, the scale factor. Yeah. Right. So so what Stata does is divide S here, and this is what is estimated. But then you don't really know S because you don't really know the true variance. Does that make sense? So it is always divided by the unknown scale factor. Okay. So yeah. So it means that I have to really short the decrease the time to explain it. But if you omit x2 here in the regression model, right? In the regression model, that means even if it's not correlated with x1, in regression model that would omitting x2 won't change anything with the beta 1 hat, right? But then if you omit that variable, then S becomes goes up because there are more unexplained variances. Does that make sense? Yeah. So beta 1, as a result, beta 1 becomes underestimated by unobserved heterogeneity, even though it's not related to x1. Does that make sense? Okay. And also for subgroups, if you divide a sample in logistic models, you can really see a lot of examples in real data. numbers that really divide the sample into two groups, for example, for men and women, and then run the logistic regression models for both groups and then compare the coefficients. It is pretty common, but it's not correct because the scale factors across these two groups can be different. Does that make sense? Yeah. So yeah, that's why you cannot compare the coefficients across subgroups in logistic regression models. Okay. And also, yeah, I'll explain that in more detail, but I hope we have time, but so this leads to the collapsibility issue in logistic regression modeling. It was not covered in too much detail in lecture, but so let's say we have y asterisk, right? And then we have 1, and then we somehow like specify the scale. Right? And this is the proportion of people who have 1 as the outcome, and x is 5. And this is the regression line. And this is the proportion of y1 at x10, x being 10. Right? Does that make sense? So let's say we have multiplied y asterisk by 2. Okay. And if that's the case, regression slope will increase by 2 times. Oh shoot, sorry, I'm not a good artist. So. Right. Okay, and this is x is 10. This is x is 5. Right. So as a result, the regression slope has been increased, right? As a result of the scaling. Right. But then the aggregate probability here has not been changed. So in this case, the effect size of unit increase in x for a person or unit or subject varies by the scale of y asterisk, which is unknown, which is affected by the unknown scale factor, right? On the other hand, the effect size for the entire sample or the population is constant regardless of the scale, because the aggregate proportion did not change, even though slope changed. So it means that it means that the estimated results or estimated effects of logistic regression is non-collapsible, meaning that the effect size on average is not the same as the effect size for a person. So in linear regression model, we just said that unit increase is associated with something increase in y, either for a person or on average, right? That's because it had a collapsibility. But in logistic regression model, the effect for the entire sample or population is not collapsible. The effect size for each subject is not collapsible for the population or to the population. Does that make sense? Yeah. All right. So to avoid the scaling issues, you should use population average effects rather than subject specific effects. I will explain what is subject specific and population average effect in a minute. The second issue here is the non-linearity of the model. So the linear effect of unit change of the independent variable of interest on the predicted probability varies by the level of baseline probability. So as x increases by 1, the effect size is about here, which is smaller. But the effect size between 10 and 11 is much higher. Does that make sense? So the effect size of x varies by the baseline probability. Where did you start from is important in deciding the effect size in the probability scale in logistic regression. Good. So the predicted probability or the baseline probability is affected both by x variable per se and other control variables levels as well. Right? So you have to think about what kind of specific person you're thinking about to say what is the effect of x variables increase on the predicted probability. Does that make sense? Yeah. I was about to, yeah.
Okay.
Okay, yeah. Yeah, all right. Before that, so the key takeaway here is you should not trust the significance of an interaction variables in logistic models because logistic regression model, so what I said earlier is basically that the effect size of x variable varies depending on other variables levels without interaction terms, even without interaction terms. Does that make sense? So the meaning of interaction terms in logistic regression models becomes different from linear models. So even if there is a significance in interaction variables in the logistic model, you should not take it as a sign of there is an interaction effect. You should, and there is no way available to obtain the statistical significance for interaction effects or logistic models. I will give you, I think the real life example is covered in the discrete change part of the exercise. There are 4 strategies to interpret logistic regression results. The first one is log odds ratio and odds ratio. I think we have covered a little bit about that, but let's download the Stata exercise and work with the real life example of that to really clarify what it means by working with log odds ratio. What you should do first is, let's skip the linear probability part. You can read through that. You can run a logistic regression. So the thing that is estimated here is whether one supports women's abortion rights or not. So agree is supporting women's abortion rights, and the others are independent variables. Age, female race, and education years. And you're interested in education years effects on the abortion rights. And there are these coefficients. And this coefficient means logit difference in supporting abortion rights as education years increases by 1 year. Does that make sense? So logit difference according to unit increase in education years. That's what the coefficient means. Good. That's the logit difference or log odds ratio interpretation. So it can be done, it can be retrieved by typing display underscore b edu. So as you can see, this beta coefficient is retrieved right here. So you can interpret that effect as 0.1546 increase in the logit of supporting abortion rights as EDUC increases by 1 year. That's logit difference or log odds ratio. And the second one here is odds ratio, which is simply the exponentiation of the coefficient. As we saw earlier, display exponentiation of the beta coefficient. And if you do that, you have 1.1672. It means that odds of supporting abortion rights increases by 1.1672 times as education increases by 1 year. For example, let's say this person's odds of supporting abortion rights was 1, right? But as this person education increases by 1 year, then it becomes 1.1672. And then another education increases, then it becomes this one. Because this is 1.1672 times of that number. Good. So this is also the same thing as 16.72% increase. This is not percentage point increase, just percentage increase, which is same as 1.1672 times increase. Does that make sense? So you are not adding this stuff up. You're not adding this stuff up, right? You're simply multiplying it. That's what it means by what I meant by you are increasing 16.72% increase, not percentage. Any questions so far? Nope. All right. And then the next method is discrete change method. So what it does, what the data does is basically you are predicting the probability of supporting women's abortion rights when age is 40 and education changes from 0 to 20 by 1 year each, and you're talking about Black women. And then if you draw the plot, then you would have this predicted probabilities at each scenarios. So let's look at these three numbers. All right. So we are looking at discrete changes in the predicted probability when education years change from 12 to 13 and 13 to 14 for a 40-year-old Black woman. Okay. Black woman, a person. So according to the regression line, P hat was intercept was this one, and age was this one, email, Black, other, educ, educ. And the P hat when educ was 12 is 1 divided by this one, this formula, right? And it is 1 plus e to for the sake of does that make sense? So you're plugging in all the numbers here. for that 40-year-old black woman who has the education years of 12. Good. So that's the predicted logit right there. And then you're plugging in the number in the place of XB. And as a result, if you calculate it with calculators, you would have this one. And you would repeat the same procedure to have right? Okay. So in that case, the predicted probability changes 0.0378 or 3.78% point. And then the difference here is this one. Does that make sense? So you can see a what?
Are those numbers supposed to be?
Yeah, 13 and 14. Yes.
Oh, no, I
Oh,
think.
yeah. Yeah, the scenario here is this one is education is 12 and education is 13 and 14. Yes. Yeah, education's so this is education is 0. So 1, 2, yeah, that's fine. Good. Yeah. Now they agree with each other, right? Yeah. So you can see the effect of discrete changes differs by the baseline probability. Does that make sense? Does that answer your question before or? Yeah. Good. Where you start from determines the effect size as well. And the third method is marginal effect method. So let's go revisit the marginal effect for a minute. You know what? I think it's that's fine. Sorry. So in the marginal effect strategy to explain or interpret the logistic regression results, you are using this formula MFX for marginal effect. This one. I'm happy to talk more about how this is coming from in my office hours, but for now, let's just use that formula. Okay? Yeah. So where P is baseline probability. So it's the marginal effect is basically what it is. So it's basically the slope of the tangent of the nonlinear curve. This one. Does that make sense? Yeah. So it means that it changes by individuals, right? Or a specific scenario you're thinking about. So let's say marginal effect of education for a 25-year-old Black woman with 16 years of education. Okay. And if you calculate the predicted probability, adding, including all the numbers, right numbers, 25, plug in 25 to in the place of age, and female variable is 1, this is 1, this is 0, and education becomes 16. Does that make sense? I think, and if you plug in all the numbers and plug in the predicted logit in the place of xb, then you would have this one. So this margins command actually gives you that predicted probability. Margins at ages 25, education 16, female 1, and race is 2. Good. As you can see, it agrees with the number in the board. It means that the predicted probability of that specific scenario or that specific person is 0.5870. And now you are using that p hat for the marginal effect. You're plugging in this number in the place of p hat. And beta hat is the coefficient of black, or coefficient of education. Sorry, we're looking at the education effect, right? So that's why I type the command display education variables b and this number and this number. If you run the command, then you would have 0.0375, which means that oh, I have to change this stuff. Sorry, sorry about that. I'll change that. Sorry. Yeah. So it means that for a unit change or infinite, so I'll just use the word unit, but it's really the infinitesimally small, like infinitesimal, like change of x.
So it's not unit of the 1 year. It's not.
Right, it's not 1 year.
It's a kind of
Yeah, it's not unit increase, but it's infinitesimal increase in x. But for the sake of simplicity, it's fine to use unit increase for this class.
it's a very small number.
Very small number increase in x is associated with 0.0374 times of increase in the predicted probability. I mean, it's 0.0374 times of that infinitesimal change in the predicted probability. Does that make sense? Good. So if I can make things straightforward or simple, is basically saying that unit increase in x is associated with associated with 0.0374 increase in the predicted probability. For this class, it's perfectly fine to do that. Interpret that effect as that. Good? Any questions? Am I making any sense so far, or? Okay, yeah, good. Percentage point, actually.
This is also percentage point.
Yes, percentage point. Actually.
Because I just would like is it more extra probability?
Oh,
Extra probability.
uh-huh.
So I was assuming this is real.
Oh, percentage point, because
Right.
it's about real percentage difference.
Okay, that's fine.
Right, yeah. Yeah, yeah. Again, this has to be straight as well. And you can do the same thing with the 55-year-old woman with the same other characteristics. As you can see, the marginal effect for this person is a little different from what we saw earlier. Slightly different from what we saw earlier. So it means that the effect of unit increase in education differs by person, for every person. Basically. So the marginal effect varies by every person. All right. The last thing is also this has to be strict. Sorry. Average marginal effects, where so average marginal effect is the average of marginal effects for all individuals in the sample. So remember that marginal effects are different across all units, right? But you're calculating marginal effect for everyone, and then you're simply averaging them out to have a single summary of marginal effects. Good. The result is this one, 0.00363, which means that an infinitesimal increase or unit increase in education years is associated with the increase in the predicted probability by 0.0363 times of that infinitesimal change in x, or 0. If you are comfortable with the unit interpretation, that is basically 0.0363 increase in the predicted probability on average. So in this case, on average is the critical phrase in that strategy for interpretation, because you are acknowledging that marginal effects can be different across people, right? And you're simply averaging them out. So you should always say that this effect is there on average. Does that make sense?
So on average means average by the sample.
Oh, what?
Average by sample.
it is, marginal effects varies by people, each individual, right? And then you are averaging them out, right? So the marginal effects, so in the aggregate sense, you are interpreting your coefficient.
So if we have
Or-
about if we have 100 sample, 100 operation, 100 respondents in our study,
Mhm.
then we average by those 100 to get the average margin.
Right. Yeah.
Regardless of their age or education, something like that.
Yeah. So they all differ. Marginal effects are all differ. Yeah. So strategies to so the comparison of these strategies. So so the reason why we don't like log odds and odds ratio interpretation, log odds ratio or odds ratio interpretation is that odds are not intuitive. People don't understand what that means, right? So it's not a good way to communicate your results with the audience. So that's why interpretation based on predicted probabilities are preferred. Unless you're not working with mobility tables and stuff like that. Anyways. But and our alternative strategies include discrete change and marginal effect strategies, but they are subject to the issue of identification up to scale in logistic regression models. Remember the collapsibility issue that we talked about? They are subject to that issue, which means that they are not identified per se. They're only identified up to scale. They are divided by unknown scale factor. Does that make sense? So, so you cannot make a substantive claims about it. Okay, so. Good. On the other hand, average marginal effect strategy is not subject to this issue because you are aggregating all the marginal effects, which means you are calculating, you are interpreting the results in the population average sense. Remember we talked about subject-specific and population average effects. Right? All the other things are all subject-specific, actually, but average marginal effects are population average effects. Does that make sense? Because you've averaged all the marginal effects out, right? Yeah. Moreover, so it has an advantage. Yeah. Moreover, it provides a summary of the effects of an independent variable in a logistic regression model that are heterogeneous by the non-linear nature of the model. So there are different effect sizes for all individuals for a variable. Right? By averaging them out, you have a single number summary of for that effect of a variable. Does that make sense? Yeah. So it has a lot of advantages. Yeah. So my personal recommendation for interpretation strategies is to add a column for average marginal effect to the usual regression table. Good. So you have the usual regression table, right? Don't use nested model. You have so basically, people typically report model 1 and model 2, model 3, and then you include demographic variables and like and organizational characteristics or whatever, and neighborhood and stuff like that. For reporting to report the regression. That's the norm, right? In regression, I mean, even in linear models, it could be problematic. But in logistic regression models, do not do that. Okay? You should report the final model results only. Instead, you should add a column about average marginal effect of that variable. So now you would have 2 columns for the regression results model. Okay. And then you still have like significance and stuff like that. Okay. Again, as long as it's not interaction terms, it's not an interaction term, you can believe the significance in the sign of the coefficient. Okay. Because it's subject to scale factor. That's my recommendation, which is not, I haven't seen a lot of this format, honestly. The most popular way to report the results is discrete changes method. But as I said, discrete change method are subject to the issue of identification up to scale. So they are in a way not mistaken in that sense. Good. Still, tables or graphs for discrete changes of probabilities can be helpful. Just like this graph. It can be helpful, but you should make a note that these are subject to identification up to scale issue. Good. Any question? Yeah.
When you talk about the predicted probability, did you mean like did you include the average marginal effect, or you are focused on the those kind of traveling?
Oh, you should report both. Okay. Right. That's the main regression table, and to help to help people see what's going on, this graph can be helpful, but it should be auxiliary, not a fundamental thing. You can include it because it's so popular, and it can be really good for posters and stuff like that. It can be beautiful, so it can be helpful, but this is still like biased.
I mean, like my question was different. With the average marginal effect, it's the path of the predicted probabilities.
Oh, what? Sorry.
With the yeah.
So if you have 0.03, for example.
So we could say this is also predicted probability.
Yeah. So it's basically an unit increase or infinitesimal increase or something. Unit increase in the x is associated with 3% increase in the predicted probability. 3% point increase in the predicted probability. Does that make sense?
Yeah.
Okay. Yeah. Good. Any questions? Yeah. I'm honestly glad that I finished all of this stuff within 2 hours. That's a win for me. Thank you. Anyways, yeah, thank you. And then I'll see you tomorrow in lecture.